Hey class, today I will be teaching you about Cantor diagonalization and why you should care about it. This video will be on the more mathematical side of things, but this is an important concept that is foundational to some really important computer science insights. But before we get into the math, I just want to take some time to talk about Cantor himself. Who was Georg Cantor? Cantor was a German set theorist, so it might surprise you to learn that he was actually born in St. Petersburg, Russia in 1845. He was the oldest of 6 children. He got his doctorate at just the age of 22, and apparently he was an excellent violinist. So Cantor's big theory was his theory of infinite sets, and even though it is widely accepted today, as we can see in this meme, it was highly controversial at the time. We might imagine a conversation between Cantor and one of his contemporaries to look something like this. Disclaimer: the following is not entirely historically accurate. Cantor says, some infinities are larger than other infinities. Then Leopold Kronecker comes along and is like, nah bro, you're crazy. Then Cantor says, there are more real numbers than natural numbers. And Kronecker's like, okay, prove it. Then Cantor goes, I literally will, and he did, and that's what we'll go over in this video. But first, let's go over some terminology. What does it mean for a set to be infinite? There are 2 types of infinite sets. One is countable, which means that the set has a one-to-one correspondence with the natural numbers, which are just the numbers you use to count, so like 1, 2, 3, etc. The other type of infinite set is an uncountable set, which, as you might expect, means that the set has no one-to-one correspondence with the natural numbers. So how do we show that a set is countable? We want to show that there is a one-to-one correspondence with the natural numbers, and we can do this by making a listing of the elements of the set. Let's do an example with the integers. We can make a listing by starting at 0, and then alternating back and forth between the positive integers and negative integers, like so. Then we have demonstrated a one-to-one correspondence between the integers and the natural numbers, so the integers are countable. Now it's your turn. Can you show that the positive rationals are countable? I encourage you to pause the video to try this out for yourself. This is a bit tricky, so let's go over this together. Recall that a rational number is a fraction where the numerator and denominator are both integers. Then, we can arrange the positive rationals in a grid, where the numerator increases along each column and the denominator increases along each row. Then we can do something similar to what we did with the integers, which is to start at 1/1, then move in a sort of zigzag pattern, skipping duplicates. For example, here the next rational would be 2/2, but since that's the same as 1/1, we can skip it and go straight to 1/3. This demonstrates a one-to-one correspondence with the natural numbers, so we have just shown that the positive rationals are countable. Now we know how to show that a set is countable, but how do we show that a set is uncountable? Recall that uncountable means that the set has no one-to-one correspondence with the natural numbers. Then, our goal is to show that there is no one-to-one correspondence between the real numbers and the natural numbers. But how do we actually do this? Turns out we're going to use proof by contradiction. Let's remind ourselves how proof by contradiction works. First, we assume some statement A. Then, we show that this assumption somehow leads to a contradiction. From this, we can conclude that A is false. So what that means for us is that we are going to assume that the real numbers are countable. Then, we will show that this assumption leads to a contradiction. From this, we can conclude that the real numbers are not countable. Now, we're finally ready to go over the Cantor diagonalization argument. First, we are going to assume that the set of real numbers between 0 and 1, non-inclusive, is countable. A quick aside, you might be wondering why we are limiting ourselves to only a subset of the real numbers, and the reason we do that is because it makes the problem a lot easier for us, and if we prove that a subset of the real numbers is uncountable, then we also prove that the set of all real numbers is uncountable. Now back to the proof. If the set of real numbers between 0 and 1 is countable, then there exists some listing of the real numbers. I've put an example here. Now what I'm going to do is highlight the nth digit of the nth real number, and we can start to see why this is called the diagonal argument. So for the first real number, I've highlighted the first digit, the second real number, I've highlighted the second digit, and so on and so forth. Then I'm going to construct a new number, we can call it r diagonal, where the nth digit of r diagonal is different from the nth digit of the nth real number. Here what I've done for r diagonal is to use the highlighted diagonal digits in order, and then add 1 to each of them. So the first digit of the first real number is 2, and the first digit of r diagonal is 3. The second digit of the second real number is 1, and the second digit of r diagonal is 2, etc. If we run into a diagonal digit 9, we can make that digit position 0 in our diagonal. Then, I've constructed our diagonal in a way such that the nth digit of our diagonal is different from the nth digit of the nth real number. Then, our diagonal is a real number between 0 and 1, but it also can't be because it differs from each real number between 0 and 1 by at least one digit. This is a contradiction, which means that our original assumption is false. So, the set of real numbers between 0 and 1 is not countable, which means that the set of all real numbers is also not countable. Why care about Cantor diagonalization? First of all, Cantor diagonalization is a foundational concept to some pretty important results in theoretical computer science. One of these results is the Gödel incompleteness theorem, which states that any sound proof system for the natural numbers cannot also be complete, proven by Kurt Gödel in 1931. Another is the undecidability of the halting problem, which states that there is no algorithm that can determine whether or not a program will halt on a given input. This was proven by Alan Turing in 1936. Both proofs feature a diagonal argument very similar to the one we learned about today. The second reason why you should care about Cantor diagonalization is that Cantor's story teaches us not only about math and infinite sets, but also about believing in yourself and persevering in the face of harsh criticism. Haters gonna hate, and Cantor certainly had some very vocal haters, and unfortunately that did take a toll on him. But now, Cantor's theories are widely accepted as an important part of math and computer science. Basically, what I want to say is that if anyone is hating on you in your life, just remember, they laughed at Cantor because he told them infinite sets, but who's laughing now? Let's summarize what we've learned today. We learned some historical background behind Cantor diagonalization, which is that infinite sets were a controversial topic at the time. Then we learned that a countable set has a one-to-one correspondence with the natural numbers, and we can show this by creating a listing of the set. We learned that an uncountable set has no one-to-one correspondence with the natural numbers, and one way to show that a set is uncountable is through Cantor diagonalization. The Cantor diagonalization argument looks something like this. First, assume there is a listing of the real numbers. Then, create a new real number that differs from the diagonal digits. Due to how we have constructed it, this real number cannot be a real number. This is a contradiction, so the set of real numbers is not countable. Lastly, we learned that we should care about Cantor diagonalization because it is an important concept in math and computer science, and the story of Georg Cantor tells us not to get discouraged by our haters. As always, thank you so much for watching. This is your CS Professor of Fun.